First of all, thanks for coming this crisp winter morning in Seattle. So my name is Luis Sezzi. I'm a professor in the computer science department here. And I should say welcome to the first TVM and Deep Learning Compilation Conference. We have 180 people registered. Not all of them wake up super early, so you're probably going to see more people coming in later. And thank you. So we had a very small gathering of a very small workshop earlier this year in June. I had about 45 people, so now we are 180. So we expect the next conference to be like 600 people or so. All right. So, and I guess it's so popular because I guess I don't need to repeat that machine learning is amazing, right? Superhuman accuracy, self-driving cars, automated scientific discovery. Wow, it's all great. This is why we're here. But let's reflect what's going on here for a second, right? In the software era, the way things work is you define a problem, you write code, and then you run on a fast machine, right? But in the machine learning era, what you do is you define a problem to solve, you gather data, you get a model template, you train on the fastest machine you can find, then you deploy on a fast and cheap enough machine, right? You do inference then. But let's look at the trends that's happening here. First, model sizes and the compute complexity is growing pretty fast, okay? And that's in inference. So in training, we have training costs growing exponentially. So it's kind of amazing that you had a, multiple, about 15 orders of magnitude higher training cost from AlphaGo to from AlexNet to AlphaGo 0. But all of this has to be contrasted with trends in microprocessor. Let's see what's happening in microprocessor land. So computer architects have probably seen this plot many times before. And the thing to note here is that we have, first of all, power stopped growing, single thread performance stopped improving a long time ago, frequency has tapered, and at the same time, the popularity of machine learning is growing much, much faster than what processors can keep up, right? So, but luckily, there's this fundamental trade-off between accuracy, between specialization and performance and efficiency. Okay, so on the left here, you have fixed function chips. They're about 10,000 times more efficient than general purpose processors, but they're less programmable, okay? And the good news here is that machine learning algorithms are relatively simple to implement in hardware, which is great, right? It's really great. And one of the things that's great is that it makes computer, so we can say that machine learning makes computer architecture cool again. Makes it so cool that now if you look at the number of devices that you want to run machine learning on keeps growing, right? And all the big names, big logos are building chips for machine learning in about 50 startups and new ones coming every week. Okay, so, and to show how extreme this is a picture of our lab. Okay, so these are all the different backends that we optimize our machine learning code for. Okay, so now this is at the bottom, but at the same time, we have a bunch of models and the categories of models and complexity of models growing and frameworks. So a huge challenge here is how to efficiently deploy deep learning everywhere. Okay, so, so you don't keep hearing only from me, I'm going to invite Gaurav Kapoor from Apple now to stage to talk a little bit about his perspective of machine learning in multiple devices. Gaurav, please.
Okay, so honestly, I'm only going to talk about what we do at Apple in Core ML and just a few thoughts on where we see it's going. So it's not the complete perspective. So let's begin with that. First of all, I'm presenting the work of many people who work at Apple, and some of them are here, so please chat with them afterwards. So what is Core ML? Core ML is actually, in all its glory, it's a model specification and an engine. And Core ML, what it does, it not only supports neural networks, but tree ensembles, support vector machines, etc. And it actually largely focuses on inference. And this is a typical workflow. You make your model in one of your favorite libraries and convert it into Core ML format. So Core ML format is similar, you can imagine, just like ONNX. And there is an ONNX to Core ML converter also. And once you have this model, Xcode and Core ML engine can just simply execute this model. So, but what is more interesting for these people is how do we optimize the performance of these models? What all things do we do? So here is your favorite neural network. So the first step what we do is graph level optimization. For example, we will analyze the graph, we will fuse some operations such as con, when batch norms, constant folding, fully connected layer, and activations are fused together. These are like the standard optimization. I think what is more interesting is this memory optimization. When you're running things on a low memory devices, you have to be very careful how many buffers to allocate, how these buffers can be shared. And finally, each of these operators actually go into the hardware level optimizations. For example, some of these optimization tends to be microarchitecture focused, so we figure out, and they're hand-tuned. It takes into account how many threads we have in the compute system, what is the cache hierarchy, what is the memory hierarchy, and everything is fully vectorized. To give you an idea on optimizing convolution kernels, we look at large number of parameters, and we may have this library of 300 kernels, for example, or more than that, apparently. And what we do, we compute large number of kernel variants per device. And when we take a neural network, what we do, we actually pick these kernels and put them in a single command buffer. And and of course, then we do a lot of software and system engineering, where we cache these executables so they don't have to be recompiled. So let's talk about something more interesting, which we released this year, is the Neural Engine. So Neural Engine, iPhone XS GPU is amazing, super amazing, but Neural Engine is even more amazing. It's 10x, up to 10x time faster, and up to 10x time more energy efficient. We're not going to talk about Neural Engine architecture here. But what we can tell you, in order to make it work, what we do is on-device compilation. So we take an ML model and we compile it on the device. Compiling on the device is also very challenging because now you're writing a compiler that has to be very memory aware. So the compiler cannot actually grow really huge. So how good is Neural Engine? So here is a video, hopefully it will work. So on the left-hand side is Neural Engine, then GPU, then CPU. Watch carefully. And this is running ResNet 50, state-of-the-art, and doing 100 image processing. So this is Neural Engine, done. GPUs keep going on, done, and CPU is continuing. So you can imagine the amount of speed difference between Neural Engine and GPU. But in real life, when we actually do these neural networks, what we do is we analyze each and every neural network and figure out whether to dispatch it on the CPU, whether to dispatch it on the GPU, whether to dispatch it on the Neural Engine. In fact, what we also do is break these networks sometimes and say, hey, this part goes on the CPU, this part goes on the Neural Engine, this part goes on the GPU. And then we use operating system primitives to minimize the context search. To summarize for our performance, what we do is, of course, we do custom hardware, we do a tight integration of hardware, OS, and frameworks, and we own the complete stack. That helps us a lot. But of course, looking ahead, there are more hardware coming. We're always looking out for more performance per watt, whatever gives us. And I'm here to learn more about TVM, and I'm very excited, and thank you for inviting me, Carlos and Luis.
So I just want to reflect a bit on what Gaurav just said. I think it's pretty clear that to make deep learning more efficient, we need to do hardware plus software optimization. And then second, there's a lot of hand tuning. So having full automation would be really a holy grail. And that's really what motivates a new academic group that we formed at UW here called SAMPLE. It's like a clever misspelling that stands for Systems and Architecture and Machine Learning and Programming Languages for Better Machine Learning. So it has 4 core faculty plus about 14 students and growing. There's crazy amount of interest in this space, and also a bunch of collaborators both in academia and in industry. And the kind of problems that we're working on here, just to give you a flavor, is at the programming language layer, we're working on high-level support for future machine learning applications. In compilers, we are building a compiler with extensible support for future models, future architectures, and optimizations. On the system side, we're looking at training both on device and in the cloud, and working at networking stack. You're going to hear a little bit more about it later today. Networking stack for more efficient distributed machine learning, for example, and training. And then the architecture layer, we're actually looking at designing architectures that are more efficient and faster for both training and inference. But something that underpins all that we do here is using automation and machine learning to optimize every layer of the stack. Okay, so we really want to use automatic learning-based design and optimization techniques here. So one way to think about this is I love this Azure picture of a hand improving a hand. So it's like machine learning making better machine learning systems. And one of the things that I wanted to emphasize is that we're very committed to open source. So the way we see open source deployment is we open source stuff when it's ready, and then hopefully the community picks it up and helps it grow, and then that forms an infrastructure for us to do better research. So we want to keep feeding this vicious, virtuous, that was not calculated, I promise. It's a virtuous cycle. Academia is a great thing. With that in mind, let's talk a little bit about open source. And open source compilers have really transformed our industry, right? If you think about GCC was the very first big compiler collection that helped bring up new architectures, people build new systems. And in fact, I spent a couple of years in my 20s hacking on GCC. Right around the same time when Chris Latin, we were in grad school around the same time, a few offices away, was ramping up LLVM. And his goal there was really to build a higher level IR to enable new optimizations and also make the infrastructure a lot easier to extend. And this really picked up. It's kind of amazing what happened in 15 years that probably LLVM generated code touches most of the machines in the world today. And the way we see is that now in the age of specialization of architectures and of systems, it's only natural to have compilers specialized in machine learning. And we see as one way of potentially trying to end the tyranny of closed deep learning systems. And to continue here, I'm going to bring the person who started it all, so Tianqi Chen, who's a senior grad student here, is going to talk a little bit about TVM and its and what it is. So, Tianqi.
Thanks, Luis, for a great introduction. So hi, everyone. My name is Tianqi Chen. Today, I'm going to tell you a bit about TVM. There are a great line of talks that will give you a deep dive on all the perspectives of the system. So to give a high-level overview, one of the major goals of TVM is we want to be able to bridge those high-level frameworks to all kinds of hardware devices and solve the challenge that Gapul have mentioned, like how do we do full-stack co-design of the system and build a compiler stack that everyone is able to use and collaborate on. So TVM consists of a few major components, including a high-level differentiable IR, which is called Relay, that Jerry is going to talk about more today. It will allow you to do graph-level optimization, such as operator fusions, memory planning, and a few other effective transformations to really make your computation workload to fit on things like specialized hardware. The second level is a tensor expression IR that's able to automatically generate code for each of the hardware backend that we are targeting for without having to ask developer to rewrite the code for each specialized backend. We have a great bunch of backend, including everything that's supported by LLVM, and we also have a code generation backend for things like Apple's Metal, CUDA, and all the major GPUs like Vulkan for other kind of mobile GPUs. And Thierry today is going to talk more about the specialized accelerator backend called VTA. So this is one thing that we are really excited about. That is an open source deep learning accelerator that really allows us to do research on how can we build new compiler stack for special ASICs, or how can we co-design future ASICs together with the compiler stack. So as you can see that the entire TVM gives you an end-to-end fully open source stack from the high-level optimization, low-level code generation, driver stack, to the hardware design itself. And we are really excited about being able to do this entire end-to-end research, as Luis talked about. So from a high level, what TVM offers to end user is this high-level API that allows you to take models from existing deep learning framework like Keras, MXNet, TensorFlow, PyTorch, and compile them to a deployable module that allows you to run your application like cat detector or other things that are minimum from the compiler stack. Like Gapul mentioned, it's very important when you deploy things on a device, you really want to build a minimum module. If you want to deploy things even on your cloud, you want a minimum container that allows you to store your service. So TVM really have this clear separation of compile and deploy stack that allows us to deploy deep learning framework on any of the platform and language that you choose. So far, we support major languages, including C++, Python, Java, and even JavaScript that allows you to run these things on your browser. One of the most exciting things that we are really excited about that differentiate TVM from a traditional deep learning compiler stack or traditional compiler stack is the aspect of automation. So traditionally, most of the existing compiler stack tries to use human handcrafted heuristics to try to basically build up rules on how do you lower and optimize code. The problem in that perspective is that really hard to come with the Oracle rules that works for all the kind of hardware. What we really want is we want to be able to bring machine learning to rescue, to actually let the system is figured out itself to specialize to all kind of hardware backends. And this is the auto TVM component. So far, auto TVM works for adapting code to each of kind of hardware, and we already see preliminary result on speed up on all kind of hardware backends. And we are actively working on basically bringing auto TVM to all the stack, including using automation for high-level optimization and using automation to actually design the hardware interface itself. And we're also building infrastructures, which we call hardware fleet, that allows us to distribute this automation so that we can really scale it up to whether you want to build it in your own cloud services like Amazon do, or if you want to actually use it to optimize your own chip, we will have a solution to build all of them end to end. One of the important things that TVM support is the diverse hardware backends. And before deep learning, it mainly runs on CPU and GPUs. And what we really want is to actually have a diverse hardware backend that allows us to run all kind of hardware that we want to support. So far, TVM runs on all the CPUs and GPU hardware backend that LVM support. We also have a source code generation backend that allows us to actually generate code on for CUDA, Vulkan, and Metal devices. And as Thierry will talk about, we also have a VTA backend that allows us to run on specialized accelerators. One of the things that we are really excited about TVM is this, we are trying to build an open source community. The idea is that TVM started as an open source project in UW Sample Lab, but now we are trying to build an open source community that can bring everybody on board to collaborate together. TVM uses Apache governance model, which means that any person who contributes a significant amount of code will be granted ownership of a project. The idea is that we want everybody to collaborate together and be able to push forward a community that everybody can use and contribute together. So far, we already have 11 committers, 29 reviewers, and 166 contributors over the world. And we are really looking forward to work together with the community to really bring this project to the next stage.
Okay, so now, to talk about industrial impact now, we brought two company friends of the project who have been working on TVM. The first one will be Vin Sharma from Amazon, who's going to be talking about Amazon SageMaker Neo. Thanks for coming, Vin. Sure. Here's the token of control.
Thank you. Perfect. Thanks, Luis. My name is Vin Sharma. I'm responsible for a team of people at AWS that work on TVM. Coincidentally, most of them are sitting here in the second and third rows, so if you get a chance to talk with them, please do today. So it's really a great privilege to be a part of this community. I've been a part of several open source communities in the past. I think it's something that is frequently underappreciated in the impact that it has, not only in kind of developing the technology, but in disseminating or diffusing that technology and the innovations in it to a broad range of people. And a large part of what I will talk about today is really three simple things: how we're using TVM within AWS and Amazon, what we're doing to make it easier for other people to use TVM, and what we will do in contributing back to TVM to make it even stronger and better and more accessible to a larger number of people. So with that said, how are we using it? So first and foremost, the journey started around the time of the inception of TVM itself as sort of looking at it as a backend for MXNet. We have clearly at Amazon and AWS a significant investment in Apache MXNet. We'd like to see that framework succeed and be accessible. It's a high-performance platform for developing models and training models. And when it comes time to deploy those models in production, we'd like to see that performance carry through to its deployment platform as well. And TVM became a very promising technology by which we could deliver that performance as MXNet models got deployed to edge devices and to a variety of other platforms. But as we went further beyond that, AWS offers a number of application-level AI services, things like image recognition and object detection, to speech recognition, machine translation, so on. We think of these as the AI service layer. And these are all based on models that have been trained by developers at AWS, and they've been essentially set up as endpoints and APIs that you can access. You submit the data, you get back the classification or the response that you get from the model. It's fairly straightforward, easy to use. But those models obviously are deployed in production. They're scaling to possibly hundreds of thousands of users simultaneously or concurrently, and we want to make sure that those models take the benefit of having a high-performance backend or compilation technology, and that's where TVM fit in as well. We saw really good success with using TVM to improve the end-to-end latency for recognition, which is one of the object detection services that we deliver. And also we're looking at a number of other technologies, a number of other AI services that we can accelerate using TVM. That leads us to the last one. It's by now common knowledge that really to be able to kind of accelerate AI from the top of the stack, from an application level service down to the underlying platform, you need to be able to have some influence over the entire stack, and we think that one of the ways in which we'd like to see that happen is through the development of a new ASIC that was announced a couple of weeks ago at AWS reInvent, our major conference of the year. It's called Inferentia, and we're working very closely with the team to be able to use TVM as one of the possible ways in which we could lower models to that platform. So that's, I should mention that. We are hiring. One of the things that, and Louis mentioned this earlier, a few months ago when we came here for the workshop, we were really excited about the technology, so much so that we felt like we really ought to make it available for a large number of people. And I'll be blunt, we did not build Amazon SageMaker Neo for the people in this room. You don't need it. The people who need it are everybody else that are building models and would like to deploy them onto a variety of target platforms as quickly as possible and don't have either the expertise or the time to be able to set up a compilation stack for themselves and work with the intricacies of all the libraries, the dependencies, the platform level relationships that you need in the entire stack. And so, to a large extent, our goal was to create a service, essentially as a new feature of the SageMaker machine learning platform of Amazon, that would allow developers who come to AWS with either a trained model that they've already pre-trained somewhere else, or use SageMaker to train the model, to be able to very quickly compile that model for a variety of target platforms, whether that platform is at the edge or in a cloud instance that AWS hosts. Our goal is to make it dead simple, to be able to just select a model. Basically, what we need is just a simple one-page, one screen in which you specify the model input, the framework, the data shape, and input shape of the data, and the location where you want the model to be deposited after it's compiled, and click submit, and it's done. Obviously, this is backed by a simple API. The API itself is a single line that says AWS SageMaker model compilation with a set of options, and then you use the Python SDK to get the model back from your job. You could integrate it into a Jupyter notebook, so you train your model inside the notebook, you compile the model, you get the compiled model output, and you can deploy it wherever you want. So really meant to make it simple, accessible, and effective. A large part of what we did in order to make this happen is the heroism of the team that you see partially here, because we had a number of things that we worked through. All of that hard, heavy lifting of setting up the infrastructure that you would do if you had to set up a compilation stack of your own is now set up as a service that's scalable, it's reliable, it's secure, and it has all the attributes of a classic AWS Tier 1 service. Yeah, and we're hiring. So what are we going to do with this? So a lot of what we did in Amazon SageMaker Neo to make TVM a part of it and to be able to deliver that alongside other open source components like Treelight, which also has a similar philosophy of being able to take an XGBoost model and compile it for a variety of target platforms, and other new things that we've added, we want to bring back into TVM and to Treelight as open source, into the open source release, into the open source project. And a large part of what we're doing is at every layer of the stack. So if you look at things that we did to enable better support of models and frameworks across TensorFlow, PyTorch, MXNet, and Onyx, as well as XGBoost, not a framework, but we should mention that here. It's not specifically tied to TVM. I left that out. Various types of model architectures today for image classification, object detection coming soon, a number of other things that we'd like to see happen. You'll see us contribute new operators, support, add optimizations, and we've got a number of folks here that will talk in more detail about it. Yida Wang's going to talk in more detail about some of the optimization work. Make sure you catch his session. But then we've got definitely a lot of collaborations that we're looking forward to with processor partners, hardware makers of processors, as well as device makers with whom we'd like to enable broader diffusion. I don't know if I mentioned this, but we're hiring. And with that, I want to turn it back to Liz.
Thank you. So let's hear from another company now. So now we're going to hear from Chen Tian, who's a technical VP at Huawei, that has also been using TVM and being public about it. So Chen, please. Yeah.
So it's really, good morning everyone, it's really great to be here. And it's nice to see we have 180 people, more than 180 people. So our company has been working on TVM for like almost a year. This is really a great technology, and we like the TVM infrastructure. So 2 months ago, the company has announced our AI strategy. Basically, it's going to be full stack, ranging from the hardware to software. So here I want to, in this picture we showed overview, but you can see how TVM has been used here. So in the hardware, we call this Ascend, that's a brand for the chip. But on top of that, we have a layer called CAN. So CAN is short for Computing Architecture for Neural Network. So in this layer, what we do is we provide chip operator libraries, high performance chip operator libraries. And also, we want people to be able to develop operators using development toolkits. So we made a lot of extensions and enhancements in TVM, and we call it Tensor Engine. But in backend, we use TVM infrastructure. So we hope that people can use TVM or Tensor Engine to develop high-performance operators for this layer. And on top of that, we support different kind of frameworks. So this slide really shows internally how we use it. A little bit more detail here. So given a model trained by different frameworks, we will have a module called model conversion. We convert those trained model into our internal representation. During the conversion, a lot of optimization will be done, and then we will execute this model or graph on our specialized hardware. So during the model conversion, we leverage TVM to basically customize certain operators for completeness and performance. There are cases where a lot of operators are available in other platforms, not available in our hardware, so we can use TVM to automatically generate those operators. And at the same time, the TVM is able to perform a lot of optimization. Of course, we also did a lot of optimization as well. So eventually, we'd like to see automatic way to generate operators. So, so far, the bottom of the slide shows that we have more than 70 operators written by TVM. Those are really production quantity of operators to be shipped to our customer. And from the development efficiency perspective, we can see over 3x improvements. But most importantly, it's about performance. I didn't mention in the slides, But out of those operators written by TVM, a lot of them are performance critical ones. And based on our experiments and testing, adding enough optimization can really bring the performance of those operators to the level that hand tuning operator can deliver. So it's about the same, and certain operators, the performance is even better using TVM. I remember a couple of months ago in the TVM workshop, TNT was mentioned it's sort of like an automatic way versus hand tune. I think we're on the right track. We believe that using TVM to automatically generate operators can essentially save a lot of resource. Well, this is some business case. Basically, we have our solution has been embedded in many different scenarios, and this is a really self-driving case. We have successful practice with Audi in level 4 autonomous driving, and the TVM generated operators has been integrated into this into the autonomous driving algorithm. Well, the result is really great. So you can see a lot of different scenarios: traffic light identification, pedestrian identification, all this stuff. And the TVM has contributed a lot in the operators. Also, we have a wide range of products we call the Atlas series products. So it's ranging from the development kit and Accelerator car, edge station, appliance. Actually, one of my colleagues here, Tiger is here, he brings some of the hardware here. If you're interested, you can stop by during break time. And so, yeah, TVM actually is able to deliver high-performance operators, and hopefully our products can make contribution to manufacturing, intelligent care, smart transportation, and so on. So basically, we want to make sure the products can make our life easier and better. So back to our contribution, while we like TVM infrastructure and we leverage that, we also made a lot of contribution back to the TVM community. At this point, we have 8 contributors and also 4 reviewers. We have working on multiple modules in TVM, and in the future, we have a lot of other things to do. Well, we realize that TVM can bring a lot of benefits. We also see a lot of challenges ahead, and we really hope that the community, academia, industry can work together to solve those challenges. And also, I hope that the TVM workshop, every year, we're going to grow Moore's Law, right? Okay, thank you very much.
All right, so now that you've heard a lot about TVM, we thought we would do a demo just so you have an idea of what you can do. So for that, I'll bring Megan Cohen, who's a PhD student at Sample, who's going to tell us a little bit about what she's been working on. Yeah. Just press the button and it magic happens.
Well, hi. So we wanted to give you a demo of what TVM can do. So here on your left, we have a video of VGG11 doing image recognition on a Raspberry Pi 3B. So this is actually using TensorFlow Lite, which is optimized for low-powered devices like the Raspberry Pi. And it's using 32-bit floating point and has, this model gives you 66% accuracy on ImageNet, and it's processing at a rate of 1.42 frames per second. So my colleague Josh trains binarized models. So we trained a 1-bit, 2-bit model and then implemented the operators in TVM. So like here's our work. So we were able to get a model that gets 62% accuracy using only 2-bit activations, 1-bit weights. And we process these at 4.67 frames per second. And we're actively improving this speed, but we're getting almost 3x improvement over an optimized baseline. Cool.
Thank you. We have one more. All right. You heard a lot about software, and what we're going to do now, and yeah, we love that video. I watched it a lot last night, so I memorized it. That's why I could use it as a gold standard for the labeling. Okay, so now we're going to go a little bit further down the stack and talk about hardware. So we have an effort going on designing a fully open deep learning accelerator that's tightly integrated with TVM, and for that, I'll bring our master hardware designer, Terry Moreau, who's just a doctor, just finished his PhD last week. Dr. Moreau, so congratulations.
All right, thank you for the introduction, Luis. I'm very excited to talk about VITA. By now, you're already introduced to this effort. The idea was that we observed that a lot of companies, and today we've seen the proof of this, a lot of companies, software companies even design their own hardware accelerators. And we found that it was very challenging in terms of putting together a usable, a programmable software stack on top of novel hardware. And so as Tianxi was developing TVM, this compiler to target all types of hardware designs, we also developed VITA, which is this versatile tensor accelerator. It's an effort from University of Washington to build an open source deep learning accelerator with programmability in mind. We wanted to make it easy for people to explore cross-design techniques that affect software and hardware co-design. And most importantly, we're targeting simple off-the-shelf FPGA designs like this board that has a Xilinx FPGA. And we've used these types of boards in class material where students were able to learn about hardware-software co-design with not a lot of hardware background knowledge. And this is eventually what we want to enable down the road. So to give you a view of the complete stack, we've developed the lower layers of the stack, including this runtime, including this flexible ISA, and this VITA microarchitecture. And we started development by targeting these small edge FPGAs that you could buy for less than $100 or $200. But there's an ongoing effort on targeting cloud scale FPGAs, really large FPGAs that can offload inference and training workloads. And down the road, we're also working on ASIC. How can we facilitate and automate the process of generating ASIC chips? But if you want to get started today with VITA and you don't have an FPGA or you don't have an F1 account, you can actually use our off-the-shelf simulator that can simulate the accelerator. And I wanted to give you a quick overview of some of the exciting things that you can do with VITA. So this is a recent research effort that we started in our group, which was to, given FPGA constraints and given model constraints, could you open up an interesting design space of hardware variants? So you insert some knobs, some design knobs, and you open up this large design space. And eventually, you compile all these designs on a cluster, you evaluate certain metrics, and you see that there are certain designs that seem very promising for this little board right here. And the idea is to then use auto TVM, which is already a component of the TVM stack, to identify which design candidate is actually doing well for a given workload. So you perform auto-tuning, and then you can characterize which design and which type of scheduling strategy works best for your needs, and then deploy this on an FPGA. And so this is something that I'm going to show later on in my talk, and I'm going to have a hardware demo running on this little board right here, so looking forward to this. So just to summarize, the goals of VITA is to produce a blueprint for a complete deep learning acceleration stack and also enable experimentations across the stack. And we really want the open source community to get involved in this effort. We're very excited to bring new industrial partners on board, including Xilinx. And we're very excited to bring to the masses industrial strength deep learning acceleration. Thank you.
Thanks, everybody. So I'm Carlos Castren. I'm one of the professors at the University of Washington and the members of the Sample Lab, along with Zach, Arvin, and Luis. And super excited about the work we've been doing here at UW. So far, you've seen a tremendous focus on optimizing inference for hardware, but of course, we want to be able to train these deep learning models at scale. And when I think about training, I think about the cloud, being able to make that highly performant, but that's not the only place we want to push training to. We also want to think about training in the edge. So how do you train on very small devices? And one of the focuses for us is not having to push a very heavy framework into the device, but use TVM to not just optimize how training goes, but really send the most compact and efficient piece of training infrastructure that can be running directly on device. And to talk a little bit about how we're approaching this, I want to invite Jared Roche, who's one of the PhD students here at UW, to talk about a new project with Relay that's focusing on an end-to-end differentiable architecture for TVM. Jared.
Hey everyone, I'm Jared. So what I'm going to talk about a little bit, so we've been showing this new stack diagram that we have, and in it we have this high-level differential IR, which we haven't touched on much today. And what we want to focus on is, as Carlos was saying, is something we've been pushing for is being able to represent more and more of the programs that we run. And so with TVM and NVM today, you're able to represent usually the part of the program that you're doing inference on. You're able to perform auto diff, but what we want to be able to do is capture things that exist outside of just the model itself. So for example, maybe a generation loop in a generative model or a training loop during training. And so in order to do this, our goal here is that we want to get this standalone training deployment, and we want to be able to apply all the great optimizations that we have. But in order to do this, we need to increase our representation of the program and capture more of the program. So what we've been doing with Relay, which is this high-level differential IR, which I'll talk about later today, is to increase the expressivity of the intermediate representation so that we can do things like optimize both the forward pass and the backward pass of the program. We can add support both in training and in inference for customized data types. We have support for the FPGA, and as our FPGA collaborators start to push on training, we can provide support on training on the device. And then finally, integrating with distributed execution and training machinery, such as Liang's P-Hub, which he'll talk about later this afternoon. And I'm going to have a lot more details on Relay today during my talk, so feel free to come and find me in the session and chat some more.
Thanks, Jared. This is an exciting project. It's exciting to see how much TVM is having an impact already, the number of contributions we're having from industry and from universities around the world. It's super exciting, but we're just getting started. As a machine learning person, from our perspective, we really want to focus TVM on three things. Making training faster, more efficient, both in terms of performance and energy efficiency, increasing the level of automation of what TVM provides, and of course, being able to provide a whole broad range of hardware targets, including new hardware like Vita. So in more details, what you see around the corner on the training perspective is a focus on automatic differentiation of Relay, large-scale training on device, and of course, focusing on new training paradigms, for example, training of accuracy, energy, and throughput. From the level of automation, we've been pushing very significantly on automatic quantization, and you heard Megan talk a little bit about that. We're thinking about how to do full program optimization. So far the focus has been on optimizing individual operators in neural networks, but what we can do now is optimize a range of operators that show up in a neural network, the underlying control flows, and even more broadly, a general workload that we might want to support on device. And going further on the Vita project, optimizing the actual hardware is a key component of what we can do with Auto TVM. So jumping more deeply into hardware, the Vita design that we've been doing so far is really exciting, but we're pushing further on Chisel as a target for this design that gives us a lot more flexibility and the ability to go a lot deeper into the approach here, all the way to an ASIC flow that would allow us to trade what we do with FPGAs and translate it into actual silicon. And of course, the design of Vita today is focused on inference, but training is the next step for all of TVM. So training on Vita is one of the next areas of investment. Now back to you, Luis.
I hope you're not getting tired of clapping. You don't need to clap every time we switch, by the way, but thank you. Thank you, Carlos. So I just wanted to say thank you to our sponsors. We've been very fortunate that our group has had quite a bit of interest. You notice that we have support from Huawei, Oracle, Intel, Xilinx. And you see all of this white area here. You can put a lot more logos here. So we can fit a lot more. So you know who to talk to. We have a fantastic crop of students to support. And here's the plan for the day. I know it's a long day, but it should be fun. So now what's gonna happen right before the first break is there'll be a deeper technical dive on TVM that TNT is gonna give. And then Ida, thanks for coming, is going to give a presentation on some of the compilation work that he's doing, compilation presentation work he's doing at Amazon. They have a break. Then the next session is going to be on automation, Auto TVM, go deeper on that. Then you're gonna hear a lot more about the Vita open source design and see a hardware demo. And then Nick Hines from Berkeley is going to talk about some of the work he's been doing on building a secure enclave around the Vita design, so you can actually have a secure enclave running potentially in the cloud and not have to review data during inference. So then there'll be lunch served here, there'll be boxed lunches, and so the next session is going to be on training programming systems and hardware, so people from Samba Nova, Intel, both Brian Radford and Justin is going to be talking about what's going on at Intel. Then Jared's going to give a deep dive on Relay. You're going to hear about distributed training in the cloud. And then Michael Taylor, who's a professor here who does work on computer architecture, is building a machine learning supercomputer, is going to give an overview. And then I have another break, and we're going to have more talks on compilers and FPGAs. So Xilinx, Graham, thanks for coming to talk about what's going on at Xilinx. And Andrew Tulak is going to talk about what's going on at Facebook. And then it'll be lightning talks. So it'll be about 15 talks, even faster paced than the keynote. It'll be a whirlwind of talks to hear. You don't need to clap every time in case you're tired. And then it'll be a social, be wine, drinks, and food here. Okay? Thank you.